The Holy Grail, a persistent hash array map tree for C++. And in the course of this talk, I would explain what each of those words means. So if you're not quite sure yet, hopefully you will be by at least the middle of this talk. Actually, starting with the first part, the Holy Grail. Why am I using that term? In fact, I've said the Holy Grail exclamation mark. Maybe that should be the Holy Grail question mark. Because what I want to examine is whether we can actually achieve a container that has properties that have the minimum number of trade-offs given what we actually want to get out of it. So we'll have a look at what those properties might be as we go through, and we'll see whether we actually achieve it. So we'll all discover this together. And I want to start with that last word there, try, because I've been pronouncing it tree, and you can see some trees in the background to try and emphasize that. It's also a good excuse for me to get one of my holiday pictures in. It comes from the word retrieve, and that's why it's pronounced tree. But some people may pronounce it try, that's fine as well. In fact, if we look at the Wikipedia article on trees, it says they were first described in 1959, so it's not a new idea. Many of you are probably already familiar with these sorts of trees. Usually some sort of string dictionary. We're going to use them slightly differently today. Says the term was coined 2 years later by Edward Fredkin, who pronounced it as tree, as we said, because the middle syllable of retrieval. However, other authors pronounce it as try, as we said, in an attempt to distinguish it verbally from tree. I'm going to stick with the tree pronunciation, partly because I just prefer historical accuracy, and partly because I'm already quite well known for catch. I don't want to be known for try as well. So with that, we'll come back to how this fits in a moment, but for a bit of background, we talk about sets. And actually, more generally, we want to look at all the associative containers currently in the standard. You'll see why shortly, hopefully. There's 8 of them currently, if I counted right. You can sort of group them quite nicely like this. And you can see that there's some quite obvious pairings there. They'll divide into the sort of single and multi versions. I'm sure you know what the differences are. But basically, if you've got multiple identities, or the same identity for different values, only the first one will be entered into a single map or set. Multi-maps or sets can contain multiple values of the same identity. But the underlying data structure is going to be usually identical in both cases. So for our purposes, we don't need to consider both pairs. So we're going to drop the multi-versions for now, to keep it simple. So now we can see the top and bottom nicely divides between maps and sets, or sets and maps. And again, the underlying data structures are usually the same. So you can implement a map in terms of a set just by having a set of key value pairs where the comparison is on the key. So again, pretty straightforward stuff. So for our purposes, we don't really need to consider both pairs. So let's drop the maps as well. And that's how we end up just talking about sets. So now we come to this indivisible set of properties between standard set and standard unordered set. So before we look at what those properties are, just an honorary mention to one other associative container, the sorted vector. So you load up a vector and you sort it according to your identity, and then you could just do a binary search for lookup. That's still a great choice for many applications. So I thought I'd mention it here, but it's not strictly speaking an associative container. We may sort of come back to that a little bit later. But between sets and unordered sets, we first of all observe that the underlying data structure, well, for set, it's not required to be, usually a red-black tree. It's got to be some sort of balanced binary tree, and as far as I know, all of the standard library implementations use a red-black tree. We will have a look at a little bit more at red-black trees later, so I won't talk about them more now. But just to contrast that to unordered set, which is based on a hash table. Then we have requirements on the types, and this may dictate what you can actually put in these things. So standard set, we have the strict weak ordering, which implies that we either have a less than comparison operator, or you can provide your own predicate for that. But we must have this ordering for it to work. And an ordered set, well, notably, doesn't have that requirement, which, as we'll see later, does become relevant. But it does require the type to be obviously hashable, either with specialization of standard hash or your own predicate, and equatable, so comparing equals. Again, provide your own predicate. So they're actually quite different requirements on the type. Most types may supply both, but then the bit we're normally interested in, the complexity guarantees. Red-black trees, or the equivalent, have log n complexity. This is on lookup, primarily talking about lookup here, whereas unordered set is constant time. On average, we usually forget that bit. Actually, it can tend towards linear in the worst case. We don't often get to that case, but that can become relevant. We will see an example of that later. So it's not perfect, but in general, this does translate to unordered set being generally significantly better performing than a red-black tree or a standard set. So where that matters, we'll usually reach for something like standard unordered set or unordered map for our associative container needs. So we have these available to us, but there's one property that I want to talk about that these don't have, and that's what's going to lead us on to the main topic of our discussion. So let's look at that next. So this word is persistence, and I've put this picture up here. This is me at the end of the London Marathon last year as an example of what we're not going to be talking about. Not this type of persistence, but also it's not the type of persistence that involves file systems, databases, any sort of serialization. We're not talking about that either. That's often conflated here. What we're actually talking about is probably best explained with an example. So just for the moment, we're going to talk about lists. So we have standard list, but lists in general, particularly in functional programming languages, have an interesting property. We'll just briefly look at. So again, I'm sure you're all familiar with how a singly linked list works, but we're just going to run through it very quickly for background purposes. So we'll have a number of nodes, each with an element value and a pointer to the next node, or previous, depending on how you look at it. And then the first one we usually refer to as the head, and then the rest, or the first node in the rest, the tail. Straightforward enough. There's the pointers. The way it gets interesting is when you want to introduce a new node at the head. So bring this new one in here. All we need to do is write the pointer to the previous head into the new node. So the original list doesn't need to know anything about this new node. So if we assume that we're going to be wrapping this up in some other type, so let's introduce those in here, we can now have two lists in memory at the same time, sharing all of their common state. So this is what we mean by persistence. The old value persists, the old container. It's still persisting while we're using the new one. So we could do this the other way as well. If we remove items, we just point to an earlier head. Again, the previous instances don't need to know anything about the new one. Now, this is not the way standard list works, but it is the way lists tend to work in functional programming languages, which is how you can treat them immutably and yet still produce new values. Obviously, you can stack up all sorts of operations that way, and when you are finished, if you only want the latest one, you can just collapse that down as if you'd written it that way in the first place. Now, obviously, in C++, we don't tend to use linked lists very often. They're not particularly efficient. Usually something like standard vector is going to serve us better, but if we want this property of persistence, that could be a really useful data structure. But this was just to introduce you gently to the idea. Obviously, the problem here is we've only got one pointer. So if you do want to do any sort of modifications further down the list, then you actually start to get into some expensive copying. But if we put two pointers in there, then we can have a tree structure. We just get a simple binary tree, which has some other problems we'll talk about in a moment, but it is particularly good for persistence. So if we introduce a new value, now this 4 here, I think that was right, we can put it in a couple of places. We can hang it off the 3 node or the 5 node, but the 5 node, because it's a leaf node already, that's much easier. We don't need to change anything to put it down there. So we can add that in as a new leaf node there. And if we're just using a mutable container, then we'd be done here. Nice and easy. If we want to make this persistent though, then obviously we can't write our new pointer to the previous 5 node. So we're effectively invalidating that. So what we do is we take a copy of that, write our new pointer into the copy. But now we've got a new 5 node, obviously we need to write into its parents node and so on, all the way up to the root. So what we tend to get is rewrite that whole path up to the root every time we make a mutation. So there is some copying, but particularly with a large tree, it's actually quite a small amount of the total number of nodes that we need to copy, and we can then share a significant amount of the common state. So that's quite a nice property. Now, said there's problems with simple binary trees in that if you load them up this way, they will tend to get very unbalanced with some very long branches on one side and not so much on the other side. Completely breaks that log n complexity guarantee. So we have strategies for balancing them. So we mentioned red-black trees earlier. That's one such strategy. I'm not going to look in detail at red-black trees because that's not the topic of this talk, but these are the rules. If you're interested, you can fairly easily create your own. So I just want to apply those rules to this tree, just for the sake of this example, because there's another side effect of this that we want to examine. So same example, but now each node is colored red or black. That can usually be done with no overhead. It's just a convenience thing. We introduce our new node at the bottom. That breaks one of those rules we just talked about, the red node invariant. Red nodes cannot have red children. So we need to start applying these rebalancing rules, which usually apply to the parent, grandparent, and uncle nodes. So you could do it fairly locally. In this case, it just means recoloring those those nodes in the immediate vicinity. And having done that, we've restored our invariant, but now we've invalidated the next level up. We've now got another violation of the red node invariant. So we have to keep applying that, again, all the way up to root. When we get to root, the root node must be black, so we just recolor that as well. So fairly straightforward. And that gives us this nice property of being, on average, fairly balanced. That's what we wanted. That's how red-black trees work. But the reason I've gone through all of this is because on the way up, if we're making this persistent, then we will have touched these additional nodes as well. So as well as all the nodes up to root, so a little bit of collateral damage. So if we're making these data structures persistent, then there's a little bit more overhead to the copying, as well as the nodes up to root. But it's still useful. In fact, again, if you go to Wikipedia, the source of all knowledge, look at the page on red-black trees. There's this paragraph at the top. It says, red-black trees are also particularly valuable in functional programming, where they're one of the most common persistent data structures used to construct associative arrays and sets that can retain previous versions after mutations. That's what we've been talking about. So they are very useful, and I've written a couple of these in the past. They work pretty well. But rewinding a bit, earlier we were talking about standard set compared to unordered set, and the performance and complexity guarantees. Generally, we want to reach for the unordered versions, the hash tables, for performance purposes. So if we want these to be performing, then we're actually adding overhead to what we already had. But it's very difficult, if not impossible, to make a hash table persistent. You end up either having to copy the whole thing or large parts of it. And you can make some changes to make it more suitable for persistence. We're not going to go there, but you tend to end up where we're going to be going anyway, with something more like the hash tree we're going to present. But I'm going to talk about it from the perspective of red-black trees and work our way from there. So what was the problem with red-black trees? The problem all comes from the fact that we only have 2 pointers in each node. Because of that, then as our overall tree grows, then the depth of the tree is going to get bigger, quite a fast pace. So for example, a tree of 15 million values will have a tree depth of about 24 nodes. So for any given lookup, there's a lot of pointer hops that you've got to go through to get down to the value that you want. And that's where the the log n complexity will get you. And it all comes from the fact that we've got only up to 2 pointers in each node. So if that's the problem, the solution must be add more pointers. And it is. In fact, we could stop there, but that raises a couple more questions. And in answering those questions, that's going to lead us to our hash tree. And that's going to actually have a few interesting side effects as well. So the first question is, we've got all these pointers, but how do we know which one to follow as we're traversing down the tree? With the binary tree, it's simple, because you just do the less n comparison, takes you left or right. But what do we do here? So the answer is, well, let's imagine we have a node with an array of pointers. So we're going to use 32. 64 is another common number, but it's usually one of those two, in fact. So imagine you've got an array of pointers, and some of them are going to contain pointers to other branch nodes, some of them to leaf nodes. How do we know which one to follow? What we do, we take the hash of the value, or the key, rather, and then we peel off the first, in this case, 5 bits from the hash. Gives us a value, 27 in this example. That's our index into the array. So we'll take out that pointer, follow it down, we get a branch node in this case. There, we take the next 5 bits from the hash, peel that off. This gives us another value, 6 in this case. That's our next index into the next array. And that may take us to another branch node. In this case, we're at a leaf, so we're done. But now, because we're using hashes, we'll obviously have hash collisions. So those leaf nodes will be containers of values. Much like with the buckets in hash tables, we may need to do some a linear search or some other type of search at the end to get our value. But usually, once we've got to the leaf, we're almost done. So that sort of answers the first question, and that's where the hash part of our title comes in. The other question is, well, how do we make this memory efficient? We've got 32 or even 64 pointers in each node, and that's going to get very big very quickly. So what we note here is that most of those slots are empty most of the time. We've only got a few pointers actually in there, not using them all. So using some sort of sparse array is the answer. So what we're going to do is just have a physical array of only the number of pointers that we need, 3 in this case, and then an additional integer that we're going to use as a bitmap to tell us what that actually maps to in our virtual array. So all of the set bits in our bitmap correspond to the actual positions in the array, and the unset bits to empty pointers. Then we just need a way of mapping those. And all we need to do is, for any given index, we'll go to that bit, and then we'll count the number of bits to the right. That'll give us our index. So if we look at that bit right on the right left-hand side, there's 2 bits to the right. So index of 2 into our sparse array gives us the result we wanted. It's simple. But then how do we count the bits? We want to do that efficiently as well. That's another interesting question. We'll come back to that in a little while as well. But where we've ended up now is something like this. So it's a tree structure in the sense of TREE, but it's also a tree TRIE, much like you may have seen with a string tree, string dictionary tree, where you peel off each character of a string to give you the index to the next level. In this case, we're using a hash, as we just talked about. And that will give us our path down through the tree to the leaf node, and then hopefully a value. So what are the properties of this data structure? So we looked at the example in the red-black tree a moment ago of 15 million nodes, had a tree depth of 24. Well, the maximum depth of one of these trees, if it's a 32-bit hash, is only going to be 6 or 7 deep, maximum. I say 6 or 7 because you've got those last 2 bits at the end, you may not want to actually follow that, so let's say 6. And the average depth for those 15 million values in that example is only 5. It's a lot better than 24. We said the leaves hold arrays of values. We'll look at that a little bit more in a moment. They're actually more space efficient than hash tables because of this compacting that we have to do as part of the storage. The complexity is technically log 32n, which sounds a bit awkward, harder to reason about. In practice, obviously there is the logarithmic aspect to it, but will tend to be much closer to that sort of constant time average lookup of a hash table than the log n of a red-black tree. But we will look at the practical aspects in a moment. And this additional thing, no need to rebalance. There's a caveat, we do need to have a good hash distribution, because the distribution of the hash will actually impact the distribution of the tree itself. But given that, the tree should be fairly well balanced to start with. So consider what that means in terms of persistence. Still got a tree structure, so we'll still have to do that rewriting to root, but now we've got much less nodes to rewrite, and we don't have any collateral damage due to the rebalancing. So this is much better than where we were with the red-black tree already. Okay, if you read the abstract on shed.com that I put up. Oh, by the way, before we get to that, the photo in the background there, anyone recognise that? It's, yep, see the waterfall from Twin Peaks. Turns out to be about half an hour down the road from here. So another one of my photos. Now, in the abstract, I made this claim. I said that, talking of hash trees, they're close but not quite as fast as pure hash tables. That's the claim. We sort of looked at the background of why that might be the case, but how does that actually weigh up in practice? Let's look at some figures. So, some performance metrics. So I did some benchmarks. My methodology, I used a micro-benchmarking framework called nonius.io. And the way that works is you'll first sort of run a few tests against the system clock to gauge the precision. So it knows how many iterations to run of your benchmark. And it will then run that enough times for X number of samples. Defaults to 100. I've done most of these at 1,000 to give us plenty of figures. And then it'll then do statistical analysis on those samples to sort of get the average and the variance, exclude any outliers. So it's doing a lot of the work for us. So that's pretty good. Using libc++ with Clang for this, the only ones I've measured so far. That is relevant, particularly because we're going to be comparing against standard set, standard and ordered set. So it's that particular implementation. Other implementations may vary, of course. And at least for our first test, what I've done is I've loaded up each of those containers with 100,000 integers, just monotonically increasing, and then we will compare them. So that's our hash tree, or HAMT, I've abbreviated it here, standard set, standard unordered set. Let's look at some figures. So here's one of the graphs. So this is the inserting 100,000 integers. On the right-hand side, in green, we've got our hash tree. Left-hand side is standard set. And in the middle, that sort of orange bar at the bottom is unordered set. Now, the y-axis is time. So that means that the bigger the bar, the worse we're performing. So we're not doing particularly well on this one. In fact, we're about, I think, 4 times slower than unordered set, 4 times slower than standard set, 20 times slower than unordered set. Nowhere near my claim. So what's going on here? Well, this is insertion. My claim was primarily about lookup, but insertion is important. When I ran these metrics, there's basically no optimization on the insert. We're paying the full cost of persistence, copying every single time we add something. And there's a copy on write optimization that we can apply because we do need to reference count the nodes. And I've done this with red-black trees in the past. It's very effective. If you're loading up an initial tree, you pretty much do the whole thing mutably because we haven't actually started using it yet. I haven't done that here yet, so we are seeing the full cost of persistence. So yeah, it can be expensive. So let's set that aside for the moment, this work in progress, and have a look at, before we get to lookup, I should also point out that if we look at the underlying data that Nonius has given us, you can see, if I can, there we go, that's the hash tree at the top. On the right-hand side, there's a lot of extra variance over there. Something's obviously going on my machine at that point that kicked in. So Nonius has excluded those outliers, but there's this whole second half has really gone out. So to be fair, we should probably just consider the first half of that. So what I've done for the next charts is to just take that data directly and produce my own graphs. So let's have a look at lookup then. So the same 100,000 integers, this time with a find. Now we've got right at the top, the orange is standard set. The green just below that, that's just confusing. The green just below that is hash tree, and at the bottom is unordered set. So we're beating standard set now. This is much better. We're starting to get there. But we are still closer to standard set than unordered set. So we're not meeting my claim yet. But we're getting there. This is promising. So what's going on here? Remember I said what we're doing is we're just loading up with 100,000 integers, monotonically increasing. And we're using libc++. Integers in libc++, the standard hash specialization is just the identity function. So our hash is also a monotonically increasing series of integers. Remember I said that if the hash distribution is not very good, then we're going to be very unbalanced. And that's what we're paying the cost of here. There are ways to address that, but they haven't been applied yet, so we are susceptible to that. So let's move on and have a look. Oh, before we do that, that was 100,000. I actually did all of the orders of magnitude between 100 and 1 million, just to see what that graph looked like. So again, the orders are the same here, but now we can see like the profile of the different data structures. So the orange line for standard set is slightly diverging from our hash tree in the first few orders of magnitude, and then sort of reconverges towards the top. But it's actually tracking, hash tree is tracking unordered set fairly closely. They've got a very similar scalability profile. So that's interesting to observe. So what I did next was I loaded up all the same orders of magnitude, but this time using strings. So now we're hashing strings. We're getting a much better hash distribution. So we're getting closer to what we want to end up with. Now let's have a look at what we've got. So the orange one at the top is standard set again. The blue one, unordered set, and at the bottom is hash tree. In this one, we're actually beating unordered set. So we're definitely in the right ballpark. Now, as I said, this is definitely a quality of implementation issue. Another implementation I would expect to beat hash tree. That's fine, but I think this demonstrates that we're in the ballpark of my claim, with some caveats. Hopefully they could be addressed. Insertion time, hash distribution, but this is what we want to aim for. I was still a bit uncomfortable about the integers, so I did one more test for this. I took the hashes from these strings, and then I used those as a integer in another set of tests. So this is another set of integers using those string hashes. And what's interesting is everything's actually much closer together in this one. I should point out, by the way, that the y-axis in these examples is exponential. So where things are actually tracking each other, they're actually diverging in practice. But we start off with hash tree winning again, but then they sort of converge in the middle. And towards the top, actually this one goes to 100 million, or no, 10 million, sorry. But towards the top, from around the million mark, hash tree starts to become the worst performing, and standard set is actually winning, actually beating unordered set. What's going on there? Well, remember we said earlier that because of hash collisions, when we get to a leaf node in a hash table, and the same in the hash tree, we're going to have to do perhaps a linear search. So at this point, we're starting to get significant enough hash collisions that that final linear search is starting to, not dominate, but become a significant factor. Now what's interesting is that's because of the requirement on the types. We don't have the strict weak ordering requirement on unordered set. So when we get to that last linear search, it has to be linear, really. That's the only way you can do it. If we're not constrained by that requirement, then potentially we could do a sorted array at the end in our hash tree and then do a binary search instead. And if we do that, I would expect our hash tree implementation to be winning at the end as well. Again, it's another opportunity for optimization that I haven't explored yet, but we're looking pretty good. So, as I say, we're meeting the claim in some areas, maybe not in others. Hope to explore those opportunities for optimization, but it shows the potential. So, I gave this talk in Aspen at C++ Now earlier this year. It's a longer talk and went into a lot more depth on the actual implementation. So I've still got these slides here because I didn't know exactly how long I was going to have left. So we're not going to go through the whole thing. I just wanted to pull out a little bit that was interesting. So first of all, we remember this one, how we map our sparse array with the bitmap. And I said that it was an interesting problem, how we count the set bits to solve that. Here's one possible implementation. This is taken from, in fact, there's a link. There's a Stack Overflow answer. It takes you to a page online somewhere that has, I don't know, dozens of possible ways that you can do bit shifting to solve this problem. I don't follow this, but I know that it works. There's no branching in here at all. It's just pure bit twiddling. It's pretty performant, but we can do better. As the comment in the middle says, actually. Most modern architectures will have a single instruction that can do this, usually called pop count. So if you're using GCC or Clang, there's a built-in pop count that will do this. You do need to compile with a certain flag to actually get that to map onto the instruction. But when you do that, it performs much better. So all the examples I gave were with this. If you use the previous example, the bit shifting, then it doesn't perform as well. Everything sort of shifts up slightly, but the basic ordering remains the same, so it's not significantly different. Then in use, what I'm doing is using the count set bits to create, or to map the bitmap to a compact index. So because I have all these indices flying around, compact index, sparse index, and so on, I'm using strong type defs internally to keep track of that, and there's some convenience functions on there. We just need to create a mask of the bits to the right of the one that we're interested in, so that's what I'm doing at the top there. And then that will give us this method, toCompact, which is just a method on our sparse index, strong type def. So I'm not going to go into all of this in depth, but here we, again, visually, in practice, here's how we use it with a bitmap, create a sparse index, and then we can get the compact index from that. And that turned out to be really useful because then through overloading, if we already have a compact index, we can go straight there. If we have a sparse index, that gets mapped along the way. It worked out pretty nicely. Then we have the thing that peels off the bits from the hash, say 5 at a time, in this case. Won't look at that in too much detail. Our node structure, going to skip most of that. When we get down to the really nasty low-level stuff, there's actually an issue with alignment here that I need to fix. But it is nasty because, first of all, we need to create our nodes big enough to contain all of the pointers or values as well without an additional allocation. And then the placement knew that into our allocation. But do that where, if this is going to be a copy of an existing node, we'll need to copy those in as well. So we're not going to go into too much detail there, but you get an idea of what that code's like. Branch nodes, similar. Okay. And then, again, actually, if you go to the C++ Now videos, you can watch that talk there if you're interested in the detailed walkthrough of the code. So I just want to get to, okay. Right, here, so the example we looked at earlier, this is our tree structure. So these are the nodes. We have a root node, and then in addition to the root node itself, we'll just need a size, so we can do in constant time, look up the number of elements. That really is at the entirety of our hash tree, all of the hard work's going on in the nodes. So because we just had those two values, we can just collect those together in its own data structure that we'll use in our hash tree, but we can use it elsewhere as well. This is actually small enough to treat atomically on most architectures. There's an implication to that. So our hash tree itself will have a hash tree data at the top there, and then just sort of basically provides an interface onto that. Again, we won't go into the details there. Right, here we go. And then we can have another type. So I haven't really discussed this part yet, so that's why I wanted to get onto this slide. This is just the test case. We'll look at the code in a second, but this is shared hash tree. And the whole purpose of shared hash tree is just to hold atomically that hash tree data. And because we can treat that atomically, then if we want to read or mutate the underlying data, what we're going to do is take a copy of it into a hash tree. We'll just do an atomic copy or an atomic exchange. And then when we're working with our hash tree, we're completely shielded from any other mutations going on to that hash tree. So it's just a shared location that we're going to get the hash tree from that we can then work with. And if we mutate it, we can then write it back, again, single atomic exchange. And we get very effective concurrency with no locking. On the condition that we are mostly sort of bound on reads rather than writes. If we're doing lots of reads, then we'll keep looping around and redoing our work. So it's only appropriate for some conditions, but they're very common conditions. So in this test, I'm not really obviously using the concurrency. I'm just demonstrating how you can use this transaction to do that. In practice, there's a helper update with that will do all the atomically fetching the hash tree, passing that to you. You can work on it, and then when it goes back, it will atomically commit it and do this in a loop. So if anyone else is mutated in the meantime, you'll redo the work. So here's the shared hash tree itself. We're just asserting that hash tree data is trivially copyable. It's a requirement for it to be atomic. And then we've got these atomic operations. Don't pay attention to the memory order stuff. That needs to be fixed. It's more of a placeholder. And there we go. The memory order stuff, again, is all wrong. Right. Yeah, so this is the loop that it's doing for the update with. It's pretty simple stuff. You do have to get it right. This is not necessarily right, but we've got it all in one place. As far as atomic data structures go, it's one of the simplest out there, and that's reassuring, I think. So I'm going to stop with that now, just to sum up, and then we'll go to questions. The claim was that we can approach the performance of hash maps without too many trade-offs. I think I demonstrated that we can achieve that, but there's some work to be done to overcome some of our edge cases. They are more space efficient than hash tables, so that's good. copies are cheap and memory efficient. And we didn't really go into this too much. Touched on the concurrency implications, but think about having a large container, associative container, that you can copy with just the cost of 2 integers and share large amounts of common state that you can hold in memory at once. When I was first working on this, it was in the context of financial data. And what you could do is load up one of these things with an object graph of market data. And then you could make small changes and have entire scenarios, sort of matrices of these object graphs in memory at once, very, very efficiently, and very, very performant as well. So there's many implications like that. And as we mentioned, can be made to work very nicely with concurrency. So that's the summary. There's a number of references, including some papers that this was all derived from. I put all the references up on my website, levelofIndirection.com/storage/hamptrefs.html. If you can't remember levelofIndirection.com, I also have extralevelofIndirection.com. That redirects there. Or you can reach me on Twitter, Phil Nash, or you can find me later during the day. So thank you very much for listening. And do we have any questions?
Okay, then I will yell at you.
Yeah, Matt.
Have you considered, given how sensitive you are to the hash function being decent, have you considered throwing it through a couple of iterations of like Murmur 3's mix just to improve the default case?
So the question was, because we are very sensitive to the hash distribution, have I considered running it through various sort of rehashing or remixing algorithms? And yes, that's almost certainly what we'd need to do to solve the problem. And I did start looking at that, and it was actually making things worse rather than better. So I need to explore that a bit better, but there are definitely approaches that can be taken there. Thank you. Yeah.
One thing I didn't understand about your sparse array. You were counting all the zeros to find out which one you look up. Is it from there you would get an offset into, like you have a 16-bit thing there, and you have 3 or 4 bits that you're looking up each time?
So to summarize the question, if I got it right, you just wanted to clarify how we're doing the mapping of the sparse array. If I go back to the, too much code here.
Yeah, there's a lot of stuff, sorry.
Right, this one.
Yeah.
So
is that yellow thing? That's only 1 bit, right?
yeah, so the top is an integer. So that's all the bits of the integer. And each set bit in the integer represents the position in your virtual array where you have a set pointer value. And then all the unset bits are where you would represent a null pointer. In the actual array at the bottom, we're only storing the pointers themselves. So the number of set bits we have in the top is the number of actual items in the bottom.
Okay, just a sec. So you've got 3 pointers on the bottom. The top array is...
So the top array is actually just an integer. It's a bitmap.
Okay, and so it's 32 to store
Yeah.
The maximum possible 32 pointers, so 1 bit each.
Yeah, so you can do this with 32 pointers or 64 pointers if you have a 64-bit integer. One of the references that I showed at the end was a games developer who implemented one of these, and he experimented with both 32-bit and 64-bit arrays, and in his case he found that the 32-bit arrays performed better. He wasn't 100% sure why, you can speculate. He did suggest that maybe it was a quality of implementation issue and you can get a better trade-off with 64 bits, but there's not a lot in it, so that's why I stuck with 32 bits. Were you clear on how that maps now, or? Yeah. Thank you. So, yes, in the middle there.
How do you handle freeing or deleting the nodes as the trees go out of scope?
Okay, so question was, how do you?
Possibly shared by different.
Yeah. how do you handle nodes that have been deleted going out of scope? So in this implementation, I'm using ref counting. It's actually intrusive ref counting, so I'm not using shared pointer. If you look at other languages that implement this, particularly Scala and Clojure, they have garbage collection. And that's usually considered the way you have to do this, but I've got it working with ref counting. Performance enough, I think. And in fact, the reference counting also is what allows us to do the copy on write, which, so I'm not doing in this implementation, but used it very effectively before. Because as you go down, as you traverse down the tree to find your insertion point, you check the shared count at each level. As soon as you've got a shared count of more than one, then the rest of that branch is shared. If you get to the leaf and you're unshared, you can do all the mutations in place. And that can save a lot on copying. So we get the benefit from shared counting as well, of being able to do that copy and write, which I'm not sure will be so easy with garbage collection. But that's how we're doing it, just reference counting. Yeah, that's.
In a implementation where you have a hash array mapped multi-tree, would it be possible to do an efficient merge operation on two such data structures?
So the question, if I got that right, is we have a, so what term did you use again?
A hash array mapped multi-tree.
Hash array mapped multi-tree.
Right.
Multiple values for the same key. So the difference between the multi and the single version is really just a constraint on the insertion. Possibly that could have implications to how you're storing it as well. I haven't really considered that yet. That would only really affect the search at the end, though, I think. And just you would have hash collisions either way, so you still need to deal with that. So I'm not sure that would give any benefit, but maybe I'm misunderstanding your question.
I'm talking about then you could construct a merge operation with well-defined semantics.
Could you construct a merge operation?
Show up in the resulting tree if they were present in either original tree.
Right. Still not quite sure I'm fully following you. Maybe we should talk about it afterwards, but yeah, thank you. Yes, towards the back.
So on the keys, are delete operations?
Sorry, struggling to hear. Let me come a bit closer.
Are delete operations for keys supported? If so, what's the performance of that?
Are delete operations for leaves supported, was the question. For keys. Delete operations, oh, okay. So looking up with a key and then deleting. In my reference implementation, I haven't done delete yet. My experience from doing this with red-black trees is that delete is by far the hardest part. I'm expecting that to be the case here as well, although hopefully not quite as much because we don't have to worry about the rebalancing. So I think it just boils down to the case of where you just create the copy with the removed item, but I haven't done it yet, so I don't know if there's going to be any additional complications, so I'm not sure I can fully answer your question. But certainly should be able to do it. Yeah?
Can you please elaborate how to use memory deallocation?
Sorry, come a bit closer again.
Can you please elaborate on how you do memory deallocation? Because the languages you mentioned, like Scala and Clojure, they run on JVM with stop-the-world garbage collector, and this is trivial. And when you do this in concurrent setting in C++, you need to use techniques like hazard pointers or stuff. What
Right.
do you use?
So I think to summarize, how do I handle memory allocation in a world where we don't have a compacting GC? Is that a fair summary? Because languages like Scala and Clojure, when you're allocating, everything is generally much closer together in memory, so you don't have to worry too much about it. So far, all I've done is just straightforward new and delete. But that's definitely one of the opportunities for optimization. Alternative allocators and being able to reuse blocks of memory. Because as you're building these things up and you're creating and then discarding copies, so you're leaving slots open that you could reuse and keep things much more closely located, which can have implications to cache readiness. Haven't done that yet, but that's definitely something that could be done. Sounds like you have a follow-up.
So basically, you block memory deallocation in malloc before delete implementation. So currently, it's not truly lock-free. Am I correct?
That's a fair point. So because I'm using malloc under the hood, technically the implementation is not lock-free because there's a lock in malloc, but that's at the point of insertion. The replacing a new instance of the hash tree, where we're just doing the atomic swap on the root node and the size, that operation is lock-free. It's that exchange between threads that are communicating on a single instance. But there will be locks involved during the insertion at the moment. That could be mitigated by using an alternative allocator. Does that answer your question? Thank you. So, yeah.
I just wanted to confirm, because everything's looked up by hashing, the elements in here are unordered, like a regular hash table?
So the question is, the elements are unordered as a statement to verify. Yes. They're effectively ordered by the hash, but it's the same principle as unordered set, unordered map. Yeah. Okay. Well, if you have any more questions, especially Ansel, catch me afterwards. Thank you very much.